Hi, Tony.
Hello.
So, were you able to solve the problem from yesterday?
Yeah, I got the right answer.
Okay, let's get started here. So as I promised last time, we talked about the curvilinear Newtonian kinetics and the equations that we have based on the Newton second law that sum of F will be equal m in the direction of a vector. And if we are dealing with polar and Newtonian curvilinear kinetics, so this equation will give us the sum of F in the r direction will be equal to MAR, and the sum of forces in the theta direction will be equal to MA theta. And as we know that AR should be in the dynamics equation sheet, which will be equal to R double dot minus R theta double dot theta dot square, and A theta will be equal to R theta dot plus 2R dot theta dot. So this is the key to solving a problem. You will need to find AR and A theta, and then you will construct the dynamics equation or the Newton second law in the R and theta direction. So let's solve this problem. It's from Hepler's textbook, so let's solve this example. So for this example, the smooth 0.5 kilogram double collar, so this is have a weight 0.5 kilogram, can freely slide on arm AB. So one of the collars can slide on AB and the other one on the circular guide rod. So it might be like there's a groove or something here that allows this pen to move like from here to this point. And if the arm rotates with a constant angular velocity, so it's constant angular velocity, so we know that theta double dot will be 0. So let's extract the information here. So we have here is given determine the force the arm exerts on the collar at the instant theta equal 45-degree mention is in the horizontal plane. So all this analysis in the horizontal plane, that means it is not vertical. So the weight is not in this direction. The weight is outside of the plane. So we will not be considering weight in this problem because it's in the horizontal direction. Because if we will consider the weight, it will be 3D dynamics. We will have to consider like you will have R in this direction and you will have theta in this direction. Like here there is R and here is theta, and you will have Z in this direction down there because the weight is going in Z direction, but we don't need to solve in Z direction right now. Actually, we can keep it here, R and Z, and we know that the weight is going down, and we will not solve in Z direction because the problem is in horizontal plane. So R theta, that will be used. Okay, so let's extract the information from this problem. So we have the instant required is theta equal 45-degree, and we know that theta dot is constant equal to 3 radian per second. And as it's constant, so theta double dot will be equal to 0. So we got the various terms. So let's now get the R. So here's R is given. R, here's the equation of R. So this is the path of the R. So R will be equal to 0.8 cosine theta, and it's in meter. And if we want to get at the instant of 45 degrees, so R will be equal 0.8 cosine 45. And this should be equal to 0.5657. And the units are in meter. Let's get R dot. So I saw many of you, when they differentiate R with respect to T, they are confused between the R dt and the R d theta. So if I'm differentiating this term with respect to theta, so this will be 0.8, and the derivative of the cosine will be negative sine, so I'll have negative here, and sine theta multiplied by the derivative of what is inside sine, so it will be d theta, which is 1. So I don't have to write this. So I know it's directly negative 0.8 sine theta. But when we are talking about r dot, so we are differentiating with respect to t, so this will be equal, it's the same thing. So this will be equal to negative 0.8 cosine, sine theta, multiplied by d theta, the derivative of this with respect to t, because I'm differentiating with respect to t, not theta. So I will have to have this outside. So this will be equal to negative 0.8 sine theta, theta dot. And if I want to get r dot at theta equal to 45 degree, so let's substitute. So it will be negative 0.8 sine 45 multiplied by theta dot, which is 3 radian per second. When you do this multiplication, it will be negative 1.697 meter per second. So let's get the the r double dot. So for the r double dot, we will have to differentiate this term one more time with respect to t, not theta. So we'll differentiate with respect to t. So it will be dr dot dt. And this has two terms. It has sine theta and theta dot. So we will differentiate both of them. So it will be negative 0.8. Let's differentiate the sine. So the derivative of the sine will be cosine theta multiplied by theta dot, the derivative of this one with respect to t. And we have another theta dot outside, so it will be theta dot squared. So we are done with the first part of the differentiation. Let's get to the second part. Plus, so the derivative of the second term multiplied by the first term. So let's put the first term as it is, negative 0.8 sine theta, and let's differentiate the second term. It will be theta double dot, because this is d theta dt, and when you differentiate it one more time with respect to t, it should give you d square theta dt square, which is theta double dot. And we know from here that theta double dot is equal to square, so all this term will be equal to 0. So all this term will be equal to 0. So let's get r double dot at theta equal 45 degree. So when you will substitute with this, it will be negative 0.8 cosine 45 multiplied by 3 square, and this should be negative 5.091 meter per second square. So we got all the terms that allow us to calculate these two, AR and A theta. So let's calculate them. So AR equal to R double dot minus R theta dot squared. So this will be, here's R double dot, so it will be negative 5.091 minus R. So the R is 0.5657 multiplied by theta dot square. So we know that theta dot is equal to 3, so it will be 3 squared. So all of these will be equal to negative 10.18 meter per second square, because this is acceleration. So let's get E theta. So E theta will be equal to R theta double dot plus 2R dot theta dot. And we know that theta double dot is equal to 0, so this term will be 0. So we'll have 2 multiplied by R dot, which is negative 1.697 multiplied by theta dot, which is 3. So this will give us also negative 10.18 meter per second square. So we got AR and A theta. So let's see how can we use them. So right now we didn't do any Newtonian kinetics. So we just calculated some kinematics, which is the AR and A theta, and we calculated theta and theta dot and theta double dot and R dot and R double dot. So we can calculate these terms. So let's now move to FR and F theta. So to do this, we need to identify where's the R direction and where's the theta direction and what are the forces acting on the system. So we need to understand the system. So if you come here, if you want to identify the R direction, it moves from the origin of the motion up to the curve, and here's the R vector. And if we want the R direction, so the R direction will be going this way. This is the positive R direction. And if we want the theta direction, it's perpendicular to R and in the direction of the increasing theta. So here's the how the theta increase. It starts from here and goes up. So the R will be something, the theta will be something like that. So here we have R and we have theta. And it says it needs the forces at the instance where theta equal 45 degrees. So when theta equal 45 degree, so this angle will be 45 and this angle will be 45. And if we draw a tangent to this plane like this, so all these angles will be 45. So it's a very direct. So let's see what the forces that we have here. So the first force that we have here, as the arm is moving from this point and going this way, it pushes, like it needs some push, some force. So there is a force pushing the arm perpendicular to the arm in this direction. So in the theta direction. So here's the B, the push on the arm, which is the required determine the force that the arm exerts on the collar. So this is the force that is required. What other forces? Once you push this arm through this collar, the other collar will have some reaction from this path. Like this path will trying to resist this B within in this direction. So we know that this is the tangent to the surface, and we always know that the normal is always normal to the surface, like this way. So this is how the forces that we have. We have a pushing force on the arm, and we have a resistance or a normal force exerted by the surface on this arm. So let's see how can we analyze this, because we need to calculate FR and F theta. Let's see what is the forces in the direction of R and what is the forces in the direction of theta. So for R, we have only, so because P is only in the theta direction, it doesn't have any component in the R direction. But N has a component in negative R direction and another component in negative theta direction, because it has an angle 45 degree at this location. So let's write the equations. Oh, it's up there. Okay. I'm trying to get this down. Oh, okay, it's not the right place. That will take a lot of time. Sorry for this technical issue. Okay, yeah, here it loads. How about getting this back? Oh my goodness. I don't know why it gets so heavy. Okay. Let's keep it as it is. We will not move anything. All right, so let's write the forces here. And let's have, oh, all right, so let's write the forces. So here we will have the sum of forces in the r direction equal to MAR. So the summation of forces in the r will be equal negative n and cosine 45, and we don't have any other forces. And we have the mass of the collar is 0.5 kilogram. So put 0.5 here, multiplied by the AR, which we got it a few seconds ago, negative 10.18. And then we can get the normal force. So the normal force will be equal to 7.2 Newton, because we have everything just divide by uh, uh, cosine 45, and there's negative here and negative here, so the direction that we assumed is the right direction. So here is n, and let's get the theta direction. So the sum of f theta will be equal to ma theta. So let's see what forces that we have in theta direction. We have p, so we have p here, and we have negative n sine 45, the component of the normal force, and this will be equal to ma theta. So we don't know p, but right now we know n, it's negative minus 7.2 multiplied by sine 45 will be equal to 0.5 kilograms multiplied by a theta, which is negative 10.18. Calculating the b will be equal to 0. That means that the force at this location will be equal to 0, but there will be some force here and some force here. Just we are calculating an instantaneous force. So the force will having some values over here, but when it comes at this location, the B will be equal to 0. So this is just like a quick example on how to tackle the curvilinear Newtonian kinetics using r theta coordinate system. Does anybody have any question on these things? I know just like two of you, if you have any questions, I can explain more if you don't understand any part of these things. So let's move to the next part. So right now, let's move to chapter 14. Chapter 14 is about work and energy. And right now we will talk about chapter 14.1, the work of a force. So what is the definition of the work? So the definition of the work, doesn't change the colors. So work is the amount of energy transferred to a particle to change its position. So right now, let's assume that we have a surface, and this is x direction, and we have a body here. And this body has a weight W, and the surface is exerting a reaction M on this body, and there is a force B is pulling this body. So let's see what is the concept of work. So the work is equal to, in general, the work is equal to the force multiplied by the displacement. So if you have a body here, and you were able to move this body to this location by a certain amount of forces, so the force multiplied by this distance will give you the amount of work. This is the simple definition of the work, and you have the force with Newton and the displacement in meters. So the units are Newton meter or joule. So joule is equivalent to Newton meter. I will be using Newton meter. However, a force F will do a work on a particle only if the particle undergoes a displacement in the direction of the force. So if you have like this B is not in this direction, like it's in this direction. So it has right now a component in this direction, like let's assume that this is theta, so it has B cosine theta and B sine theta. So which one of these components exert work to move this particle? Does anybody know the answer for this question? Go ahead if you know it.
Would it be the P cosine theta portion of it?
Exactly, because this is how the body is moving, like in this direction. But if the body make a movement in the vertical direction, so this one is the one that make these movement. If the body moves like somewhere here, that means that it makes a movement in this direction and also a movement in this direction. So both of these exerted a work to move this body. So what about the normal force, assuming that the body only moved in the x direction, like this, without any movement in the y direction? Does N and W exert work? Does anybody know the answer? Go ahead if you know it. Like I have the body move in this direction, and it doesn't have any movement in the y direction. Does W and N exert any work?
Would it still exert work since it's kind of keeping it from moving up or down?
No, actually, because it doesn't move. Like if the body, if there's a certain amount of force on the body, but these forces didn't allow the body to move in a certain direction, so it doesn't exert work. Like if this body only moved in this direction, like come from here and go here, so just in X direction. So this is the only force that makes work. The W doesn't make work, and the N doesn't make work because the body didn't move. So what if, like, for example, if we have this body on an inclined surface like this, and here's the weight. The weight is always going down. It's not inclined. And um, and the assuming that the body is moving in this direction. So here's the MA direction. So right now, a components of the weight, like let's assume that this is the weight, and this is, let's assume that this is theta. So this angle will be theta. So you will have W cosine theta in this direction, and you will have W sine theta in this direction. So the W sine theta will exert work. Let's assume that there is not any force in the XY direction. Just the body is set on an inclined surface. It doesn't have any external forces. If the weight, let's assume that this is a smooth surface, it doesn't have any friction. So, and the body cut a distance S, so it will be W sine theta multiplied by S, just this component. Okay, so just like if the body has a friction, like if the surface has a friction like this way, so the friction will exert negative work, and it will be in this direction, and it will also multiply mu F multiplied by N multiplied by S, and it's a negative value. So let's explain this with like and more in details. So let's keep this up here and let's write down there. So let's find the scientific expression of the work. So here, if you have the body like this, and assuming that you have a force F that has angle theta with the direction of the movement, like let's assume that this body moved from here to here. So this is S, and this is the direction of S. So the definition of work is saying that F, like the work, will be equal to F cosine theta multiplied by S, the angle between the S and the force. So, and this is true because if we want to look, this body is moving in this way, and the forces that only do work is only F cosine theta. So let's see how this will be formulated in terms of vector algebra. So let's write them in terms of vector. So the definition of this thing is equal to W, and let's assume, let's call it, we will call W, sometimes we call it U, work, and we call it U from 1 to 2, from point 1 to point 2. So let's make a general thing here, like a curve or something, and you have something like that, and here's the origin O, and this is position 1, and this is position 2, and we have our particle at some random location here. So this is our particle, and we have the force is acting this way, F, and here is just like a tangent, and this is the angle theta. And let's assume that this is the position 1 is R1 vector, and here's R2 vector. So let's find a general formula for the work. So let's assume that we got a very small tiny piece here, like that the body makes this a small distance, and this small distance is dr, like let's call this vector is dr vector, and the force that we have is like F like this. This is the force vector. So the work exerted here is du because it's a very small amount of work. It's equal to the F vector dot product by the dr vector. So this is the definition of the work. Because as you know from the definition of the dot product, we know that it's equal to the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by cosine theta. So let's make this. So this is the definition of the dot product. So, and also this is the definition of the work, like the force vector multiplied dot product by the dr vector. And the magnitude of dr, because it's a very small, it will be equal to, like, let's assume that this is the length of this arc is s. So dr will be equal as a magnitude, it will be equal to ds, like this piece of the curve. And let's assume that the particle starts at position S1, and this S1 is measured from origin here, and here's the position S2. So this will, this will be equal to the F as a magnitude multiplied by ds as a magnitude, the distance traveled on the curve, multiplied by cosine theta. So let's get the total amount of work from point 1 up to point 2. So if we need this, we will need to integrate, like from 1 to 2, it will be the integration from S1 to S2, like putting an integration sign here, and this will be F ds cosine theta. So this is the most important rule here, that the work from 1 to 2 is the integration of F ds cosine theta. So is F, if F is changing with the path, like F is given as a function 5s squared plus 2s plus 1, so you will have to put it here and integrate it with respect to s. So this is the how the function. But if F is constant, you can take it out from the integration, and this will be equal, and we will see it, it will be equal F s2 minus s1 multiplied by cosine theta. So if this is constant, you will take F from the integration, and here you will have S1, S2, and you will have the S cosine theta, and assuming that theta is constant, so this will be F cosine theta multiplied by S2 minus S1. And this is something similar to this, like this is, the difference is S. So does anybody have any questions so far on this formula? Okay, so let's now see if, like, if we want to get this integration from the curve, like we know that this integration, the definition of this integration means that if you have s on the x-axis and f cosine theta on the y-axis, and here's the relationship between them. If you want the work from S1 to S2, here's S1 and here's S2, you will have to get this area. But make sure that this is F cosine theta, or the force is in the same direction of the S, because if they are in the same direction, to the theta between them will be equal to 0, and cosine theta will be equal to 1. Just make sure about this. All right. So let's now see the work exerted by different types of forces. So let's put one, the work exerted by weight. So work of the weight. And let's assume that we have XY axes. assuming that the y is the vertical direction, like this is the direction of the gravity, negative g, and we have the path like this. And here is our particle will have to move from S1 to S2, like you have maybe, here's the ground, and here is a table elevated from the ground, and you have like a soccer pole here, and you will elevate this soccer pole and put it on the table, so like on this path. And the particle at any random location, like here, will have the weight acting down, W. So let's see what is the work exerted by the weight on this particle. So if we want to write the weight force, so like, how about if we like trying to estimate or guess what is the force exerted by the weight without any calculation? Like here you will have, let's assume that this is y1, that this is y2, and this is x1, and this is x2. Can anybody know the amount of work exerted by the weight if it's like this is a soccer pole and you move it from here to here? Does anybody know what is the amount of work that will be exerted on the body to move it from S1 to S2? Like just like any guess? Okay, so let's assume that this body moved in the y-axis delta y, because you moved it from here to here, and you moved it from here to here, and this is delta x. So this is the distance perpendicular to the weight. So there is not any energy exerted in this direction, or sorry, any work exerted in this direction, because you only have to overcome this direction, like the vertical direction, and the weight is going down. So it's the weight multiplied by the distance delta y, and it's negative because we are going up. This is the weight is going down, and the y is going up, so the theta between them is negative 180. If you got cosine theta, it will be -1, so it will be a negative work. So let's see how can we prove this like using diversity principles. All right, so let's get the weight force. So we have the weight vector equal to negative W, the weight of this body, in the direction of the J, like, let's move the negative here, and it's in the direction of J hat in the negative direction. So we have the weight as a magnitude, and the direction is going down. We know that the unit vector here is J hat, and the unit vector here is the I hat. So how about the dr? If we want to get the dr vector, so we can use this equation. So the dr vector, let's assume that we take a very small tiny piece here, and this is the dr vector. It has a magnitude of dx in the I hat and the magnitude of dy in the j hat. So the dr vector is equal to dx in the I hat plus dy in the j hat. So right now, if we want to get the work u from 1 to 2, it will be equal to integration from r1. Let's assume that this is r1 and this is r2. And this will be f vector dr. So let's see how can we do this. So we have the f is negative w multiplied by j hat, and this is dot product by the dx I hat plus the dy j hat. And this is from r1 to r2. So as we know from any dot product, the only values that remain should be in the same direction. So j, so w is in the j hat. If you multiply it by the I hat, so it will give you 0. And if you multiply j hat by j hat, it will give you a 1. So this is how the dot product means. Like, because you have the I hat in this direction, and you have the j hat in this direction. If you multiply them together, the theta between them is 90 degrees. So if you get the cosine theta, it will be 0. That's why. But if you have j and j, so it will be a 1 because the theta between them is 0. So the only components that we will have here is the negative w in the direction of j multiplied by the dy in j. And this will be equal to negative, when you multiply the resultant from the dot product is a scalar quantity, not a vector quantity like the cross product. So this will be negative w multiplied by dy, and all of this will be integrated from y1 to y2. Here we change it from here because any integration in the x direction will be 0 because I multiplied by j will be 0. And this will give us negative w multiplied by y, and we will have to put y1 to y2, and this will end up negative negative w multiplied by y2 minus y1, which is negative w multiplied by delta y. So this is how we prove the force done by weight. So we know, like right now, the work exerted by a weight will be equal to negative w multiplied by delta y. So let's have a deep look on this. Here is our ground, and here's our table. If you are moving the soccer ball from the ground and put it on the table, so the w will go down. So the w is keep going down, and you are keep going up. So this is a negative work. Negative work. But what if the soccer ball is on the table and you want to bring it down? So the weight is going down and the distance is going down, so the angle between them is 0. So it's a positive work. So this is how it works. If it's negative, so it's not always negative. It depends on the motion of the weight with respect, the motion of the body with respect to the weight direction. So if the body is going up, so you will have to exert effort, negative, to move it up. But if the body is here, you don't have to exert effort. You just like will release it and it will go down by itself. So it's a positive work. So this is how the weight done by work. And just like for your record, the weight is not a vector quantity. So sorry, the weight is a vector because it has a direction. The work is not a vector quantity. It's a scalar quantity, but it could have a positive or negative direction like this one. If you are exerting effort to move the body in upper place, so you are putting some energy, you are transferring energy from you to the body to move it. But if the body's here and you just let it down, so it's a positive work because the body is exerting this work because you don't have to exert the work by yourself. So this is just like a quick note. Let's write it here. Work is a scalar quantity, but could be negative or positive. So let's move to the second type of work that we have here is the work done by a spring. All right, so if we have a spring unstretched and there's a body here, you put some force to stretch this spring in this way. So this is the exerted force. So what the spring will do? The spring will resist this force by force inside the spring. And let's see how can we we calculated this force before, but let's review how we can calculate. Let's assume that this body is right here right now. And this is the force that you put on this body. So the force in the spring, this Fs here, in this body, let's assume that this is the unstretched length. Unstretched length means this spring doesn't have any force, but once we submit this force, this spring move, and so this part is how much stretch that the spring is getting, and this is the direction of the movement. So let's assume that this is how the S increase. So as we know from before that the F in the spring equal to the K of the spring. The K is the stiffness of the spring, like this, and you have a force like this. The spring, any spring has a K, and this K is it's like depends on the material of the spring. Like let's assume that your home has a column, a wood column. So this column is a spring. It's not a real spring, like it doesn't stretch, but we assume it as a spring, and it has a very, very high K. But there is a delta when you put some load on these columns will have some delta. And this is how much force that this column resists the forces. So dk is the stiffness of the spring, and it has Newton Newton per meter. So there is the units, and k multiplied by delta. But right now our delta is s. So an s is a changing because we are measuring the s from the unstretched length. So it will be k multiplied by s. As the s increases from the unstretched length, the amount of force resisted by spring will be increases. So right now let's take a very small piece here, like this part, ds, and let's assume that the spring moved from S1, the unstretched length, up to an S2. Let's see how much work exerted by this spring. So the U from 1 to 2 will be equal to the integration from S1 to S2, and we have here the force Fs ds. So why we didn't put cosine theta here? Because the F and the S are in the same direction or are in the opposite direction. So, but it's always in opposite direction. Let's, as I told you from before, if you have a particle here, and this is a spring, if the particle, and this is the unstretched length, if the particle is moving this way, the spring will be pushing back this way, F spring. If the particle is moving away, so the spring will be pushing back. The spring, we need to get back to its normal stretched length here. So the Fs is always in opposite direction of the particle and has negative work. So let's see how can we do this. So this will be, if we integrated that, it will be equal to the integration from S1 to S2, and we have Fs is equal to negative K multiplied by S. Why is negative? Because it's always in a direction opposite to the direction of movement. So if the spring is moving this way, so the Fs will be going this way. So the angle between them is 180, and if you get the cosine 180, it will be -1. So that's why we have negative, and it's always negative. And we have ds here, and this will finally end up with, if you integrate this, it will be -½ multiplied by k s2 square minus s1 square. So this is the force inside the spring. And actually you can get this force from, if we have ds on the x-axis, and we have fs, which is k multiplied by s, and we know what is the function between them, and we want to know the work exerted from S1. Let's assume to make it, let's make it linear. S2. So if you got this area and put a negative sign in front of it, so it will be the work exerted by spring. And you can actually calculate this area. Actually, this area, so U from 1 to 2, it will be equal to, this value is KS1, because this is the function, and this is KS2, and this is these height. So if we can get the average height, which is KS1 plus KS2 over 2, multiplied by this, which is S2 minus S1. This will give you a half, and let's put -1 because the work of the spring is always negative, and we will have K as a common factor, and you will have S1 plus S2 multiplied by S2 minus S1, and this is will give you -K S2 square minus S1 square. So this is the same concept. So this is how the spring force look like. Does anybody have any questions so far on the spring? If you are given a spring in the problem, you know how to, just like you will need to substitute with this, or just like prove it to you, how can we get this value? So number 3, which is the easiest one, work of a constant force moving constant force. So here's our rule. The U from 1 to 2 is equal to the integration from S1 to S2 F cosine theta ds. So if F is constant, you can get it outside the integration, and you can get the cosine theta, and this will be from S1 to S2. This will be F constant cosine theta S2 minus S1. So this is if the force is constant, like the example that I showed to you a few minutes ago. If you have a body here and you have a force F constant, and this is angle theta, and this body moved from 1 to 2, so the work from 1 to 2 will be equal to FC cosine theta multiplied by S2 minus S1. So this is most all of the types of the forces that you will see in this chapter. And the main thing is that you will have to know how to calculate the work exerted by a weight, which is always -W multiplied by delta Y, and the work exerted by a spring, which is always negative half K multiplied by S2 square minus S1 square. So in these S's should be measured from the unstretched length. So you will have to find where the unstretched length and measure this S. Does anybody have any questions so far on this work concept? Okay, so let's overview this problem. I promise that I will solve it in detail in the next lecture. So this problem is saying that you have a body with a weight of 100 kilogram and rests on a smooth inclined. So it's smooth, that means there is no friction. If the spring is originally stretched 0.5 meter, so like let's assume that this is how does the body look like, and this the unstretched length. So in this body starts at a stretched length of 0.5 meter. So this is S1 equal 0.5 meter. If the spring is originally stretched at 0.5 meter, determine the total work done by all forces acting on the block when the horizontal force equals 400 Newton. So it's a constant force, pushes the block up the planes, S equal 2 meters. So this moved 2 meter from here. So this is 2 meter. So from the unstretched length, it will be 2.5 meter. And your body came here. So this is how the body moved. So what we will have to do is to get the work done by the weight. So you will have to have the weight like this. It's better to draw a free body diagram. It will help you to solve this problem very quick. and then you know that the body is moving this way, so you will have to analyze the weight in this direction and this direction, and only use this direction. And the weight has a negative because it's going down and the body is moving this way. And the spring is always negative, and you have the S1 is equal 0.5 meter and the S2 is equal 2.5 meter. So you can get the work done by the spring. And then you will have the force P is a 400 meter and it's pushing this way. You will have also to analyze this force in a direction of the motion and get the B cosine theta and get the B from a constant force. So it has all the types of forces that we talked about, and we will solve this example in detail next lecture. So that's all for now, and see you, Tani. See you tomorrow.
See you tomorrow. See you tomorrow, Dr. Nafal.
See you.